Today we are going to see about proportional derivative controllers. So the next type of controller is what? It is the proportional derivative controller. Okay, so these are the controllers which are used to improve the performance of the control system by improving the stability of the control systems. In the previous case, we were learning about proportional integral controllers, which keeps on improving the steady state, that is by reducing the steady state error and do not touching the stability of the system, right? So here the derivative controllers are those which are used to improve the performance of the control systems by improving the stability of their control system without making any changes with the steady state error. Okay, so what happens? It increases the steady state stability without increasing the steady state error. Okay, so here also PD, that is proportional derivative controller, is what? Actually, the proportional derivative controller is the combination of proportional controllers as well as the derivative controllers, right? PD controllers, they are the combination of what? The proportional controllers and derivative controllers. Okay, so the definition can be also written as the proportional derivative controllers is proportional to the error signal and derivative of the error signal. That means U of t. U of t is the output of the PD controller now. Okay, U of t is directly proportional to the error signal E of t plus the derivative of the error signal E of t. Okay, so E of t, that is PD controller's output, is directly proportional to E of t plus derivative of E of t. Okay, so you all know that U of t is what? It is the PD controller. In the case when we are discussing about PD controllers, if we are discussing about PI controllers, U of t will be representing the PI controller. Okay, so here U of t is representing the PD controller and E of t is what? It is the error signal, like how we were learning for PI controller also. Okay, so now also we are supposed to remove the proportionality symbol. Okay, so how is it possible? So we can remove the proportionality symbol by applying the constant to the above equation, right? Therefore, U of t is equal to k. I am applying a constant for an error signal. Okay, and also I am going to apply a constant for the derivative signal also. Okay, d by dt of E of t, right? So in order to differentiate the error signal and the derivative error signal, I am going to introduce the constant k as kp and k in terms of derivative. I can write it as kd. Okay, so what is kp? Kp is the proportional constant. Okay, and kd is the derivative constant. So now in order to find the transfer function, we are supposed to convert the time domain into frequency domain. That is very important. So for converting the time domain to frequency domain, we are supposed to introduce Laplace transform on both sides. For the above equation, let's say the equation to be equation 1 here. Okay, so consider the Laplace transform on both sides for the equation 1. That means you can write as LT of u of t is equal to, LT is what? Laplace transform of Kp dot E of t plus Kd dot d by dt dot E of t. Okay. So now from the time domain, we are supposed to write it as the frequency domain. So for that, u of t becomes u of s is equal to, what happens, e of t. When you are taking Laplace transform for e of t, it becomes frequency domain, right? Error signal, that is e of s plus, so don't forget about the constant. You have the constant Kp as it is, dot E of s plus Kd as it is. Then d by dt of E of t can be written as s times E of s. By applying the formula, Laplace transform of d by dt E of t is equal to s times E of s. This is from the Laplace transform formula for what? Derivatives. Okay. So U of s is equal to Kp dot E of s plus Kd dot s dot E of s. Let this equation to be equation. So I'm going to write the equation one more time for your reference. U of s is equal to Kp dot E of s plus Kd dot s times E of s, right? So now E of s is common to both the terms. So take E of s outside, therefore it becomes E of s dot Kp plus Kd dot s. Okay, so now the transfer function can be written as, the gain can be written as u of s divided by E of s is equal to, you are taking this E of s to the left hand side. That means it becomes Kp plus Kd dot s, right? In order to get the 1 plus arrangement, we are supposed to take Kp outside. So that means Kp becomes, the above equation becomes Kp dot 1 plus Kd divided by Kp dot s. It is nothing but the same equation. So for your understanding, let me multiply here. That means Kp, when it goes inside, it becomes Kp plus what? Kd dot, actually it is Kp, right? Kp divided by Kp dot s. So Kp and Kp will get cancelled. Here you will get Kp, which is nothing but the above equation. It says Kp plus Kd dot s. Okay. Okay, right. So now, instead of Kd by Kp, you have the total derivative constant. Okay, so replace Kd by Kp as Td. Okay, in the above equation, it becomes U of s divided by E of s is equal to Kp of 1 plus Td dot s. Okay, this is going to be your gain equation. So you are going to apply this Kp1 plus Td dot s in the control systems. In your control systems, what happens? So the closed loop control system, it becomes Kp of 1 plus Td dot s, which is the product of the error signal E of s. And what is it? This is the proportional derivative controller. The output is what? U of s. So this is nothing but the unity negative feedback closed loop control system.